Hi, welcome back. So I want to have a look now at using the voltage divider as part of a full conversion process. Now you'll be familiar with, I can work out voltage divider values, I can work out ADC values, but putting the two together requires a bit of design decision thinking, okay? And that's really critical that we understand how to put the two together, because that's what you do in real life. So let's just have a look at this. What I've got here is I've got a sensor of some description. It could be any resistive sensor in a voltage divider. I'm not amplifying it in any way, but what I'm going to do is stick it straight into an analog to digital converter. And we'll just look at the criteria here. What we've got is we've got an LDR in sunlight, which is 400 lux. We've got a voltage, well, a VCC, let's just call that of 5 volts. And I'll just highlight that so that we know that we've changed that coding. Right, that text. So we've got 5 volts, we've got a fixed resistor value of 10K, and we've got a voltage reference of 1.1 volts. So let's just have a look at what we've got. Here's our full process. So let's just think, what have we got? We've got a voltage reference of 1.1 volts. So this belongs over here, 1.1 volts. And we've got a voltage coming in of 5 volts. Cool, okay. Now the design decision is to think about, well, which way round does this voltage divider go? So let's think about it. We're measuring lux, 400 lux, which is sunlight. And so I'm going to look at my graph for the LDR. I've chosen an RP12, fairly old sort of LDR, but sort of very common. And as you can see, it's a straight line because it's a log graph. Now I'm looking at 400 lux. So here's 10, here's 100, and here's 1,000. So 400 is around here. So let's just pop this into 400 lux here. Okay, and that of course equates to a value of 3 on the y-axis. Okay, so that is a value in K ohms. It's not 3, of course, because this is 1K. So this is 300 ohms. So we've got 300 ohms at a lux of 400. So this is where we're sort of centering our measurements around, okay? Now, with our voltage divider, how do we figure out which one of these is going to be the high value or the LDR and which one is going to be the fixed resistors? Because I could have, as you can see in this diagram here, I could have the LDR on the top of this, or I could have the LDR on the bottom of this, okay? So that's cool. Now, of course, we know now that we're working with the LDR at around about 300 ohms. So I'll just pop this 300 ohms in here. And this will help us think about our design decision. Can you see what's happening here? Let's put that in there. Okay, is that in a voltage divider where we've got 5 volts and ground, and if this is a low value and this is a high value, then the output here is going to be quite high. This is going to be around about 4.8 something volts, actually. And in this situation where this value is high and this one is low, there's going to be quite a low voltage down here. Okay, so in actual fact, it works out to be about 0.15 or something like that volts. So that's what we've got here. Now let's just pop this. Well, this is how we're thinking about it, about feeding it into our analog to digital converter. Of course, the transfer function for this analog to digital converter is like this. So what's happening is we've got this ratio. Okay, so we could put 4.85 volts in here, and we could have a voltage reference of 1.1 volts, and of course the ratio is about 4 to 1. So we would expect this ADC value then to be something like about 4,000. Well, of course that won't work because our analog to digital converter is 10 bits. It cannot exceed 1023. So yes, this is not a formula. It is actually a model for how this device works, and it has some very strict limitations. Am I sounding a bit repetitive about this? That's good. Okay, so that's always what you're thinking when you're looking at this, is what are the criteria that I can put into this? Because it's not just a formula that we can bang around and do anything we like with. So what I'm going to do is, if I've got 4.85 volts coming in here, and of course that exceeds the 1.1 volts, so this is going to max out at 1023, all ones. Now, the other side of the coin is, of course, I've got quite a low voltage, about 0.15, 146, something like that volts coming in here. Then, of course, this is going to work. It's going to work quite nicely. We're going to get some value here, which makes a lot of sense. So we've got to figure out which one of these is going to be R1. So R1 is the LDR. So we're going to put R1, the LDR, we're going to put that at the bottom of our design here. and we're going to put R2, which is the fixed value of 10K up here. Okay, so yeah, just so that you can get an idea of the simple sort of design decision making that we're making when we're doing these sort of designs. So which way around should our voltage divider circuit be? Well, we've figured that out. Okay, it's going to be this way around. It's going to give us a low voltage out, which is going to work with our voltage reference. The value converted by the ADC, well, that's pretty trivial. I think you should come up with a value of 135. You can let's just check that out. Is that right, actually? Let me think. What's it going to be? It's going to be, of course, 0.146 volts. Let's get my little calculator here. It's got something on the screen. 0.146 volts, divide that by 1.1, our voltage reference, and then multiply it by 1023, and that gives us a value of 135.78. Of course, it's truncated. Okay, again, this sort of thinking also about what it means. We're working with integer type values in a register. We don't have decimal points. We're just, it's truncated. It's 135. Remember, this is our voltage resolution, the fact that some voltage range will equate to 135, and it's not quite at the level where it would become 136. So it would require a little bit more voltage than that, just a little bit more to get into that 136 value. Okay, so those are the sort of thinking we're doing around here, and it's this dynamic range sort of issue we want to have a quick look at. So here what we've got is we've got these different values from the graph. If we've got 10K in and looking at a lux of 10, we've got 90K on our graph. So what that equates to is 4.5 volts. So you can see that these values here, we can't actually work with these values of lux in our current system, okay? So they're a no-no. We really can't work with those, because they would exceed the capability of our analog to digital converter. Of course, if you want to work with low values of lux, then you're going to think about what's going to work at this part of the graph where these values are quite high, and you might change this 10K resistor. Yeah, so that's quite a good way of just starting to think. And you can see why I put my little man here with his little hands balancing these ideas, because that's what you're doing in engineering. You're thinking about one thing and how it interacts with another. So it's never as simple as just working out a solution, okay? There's always things to weigh up in your mind. Of course, our range will be quite useful around a lot of this. So that's quite good. Now, I want you to think also about the fact that we've got a log-log graph here, and our Atmel microcontrollers, they don't work in decimals particularly well. We have to turn everything into doubles, which is really a float in a normal PC, because it's only 4 bytes of data, not 8 as you would expect in a PC, which gives us a sort of, I think probably about a 6 digits of decimal points when we're working with floats. Probably quite satisfactory. Of course, it's pretty hungry on calculations. So what you could do, of course, is you could think about this in terms of, if we look at our previous graph of an LDR, and you can see it's logarithmic or exponential in shape. So what we're going to do is we could, if we're only working in a small part of the graph, we could actually look at it and think of it as a straight line. We could map a straight line between these two values and just use that. That would be close enough for the readings we want. And of course, we might not do that over the full range, because a straight line would not fit very well on our graph, but we might break it up into a couple of regions and do some simple little maths using integers, just in straight lines on a couple of regions, and that would be fine for many applications. So that's one way of working with it. So that's a good way. Break it up into regions and do some straight line approximations. So that's the way we'd use it. Oh, yes, I can't see in this light. Okay. So, oops, I'm just trying to get this to spell check for me. And I'll just highlight this. So what are we doing when we're doing this? Is we're thinking, and these are the sort of problems that we have to tackle. I'm thinking here about another situation where we've got a car. We've got some sort of potentiometer connected to the lever for the accelerator, okay? So we'll get some resistance value here, which will feed into our controller, and it will become a voltage, which is then converted by an analog to digital converter. So I'm thinking, hey, I've got this potentiometer, and say it's got a value now. I've just changed this, it's 4K 7 ohms, not 47K, which is in the original notes. So I'm thinking, you know, what is this? What are we going to do here to choose this value of R? What's going to be a suitable value for this? So I'm going to think about, what do I know in this problem? Well, first of all, I know that this is 4K7 up here. And when this is 4K7, I want it to be the reference voltage in my system, which is 1.1 volts. So I'm just thinking my voltage reference is 1.1 volts. And you can see that there's fairly clearly a linear relationship here. This goes from 0 to 4K7. This goes from 0 to 1.1 volts. So we've got a voltage divider. We have to figure out this value. And of course, it's fairly straightforward because what we've got is we've got 12 volts coming in here, typical car voltage, for instance. And then that means that if we've got 1.1 volts at this maximum level here, that must mean that we've got 10.9 volts across this resistor here. So this is what it's going to look like. And now you can start thinking, well, it's just actually an application of Ohm's law. So we've got our value of current works out to be about 0.2 something milliamps, and feeding that into this resistor, we get a 46,572 ohm. We're not going to choose that. What's available is a 47K resistor. So we just worked out what this 47K ohm resistor is. And these are sort of problems you work out. These sort of problems are this whole idea here of balancing and weighing up all the different factors that you can think of and putting them in together and trying to get a perspective on what's going. And the way I do that often is I draw a diagram to just put everything on the diagram so I know what I'm looking at, and then I can start thinking about what's going on. So that's really clearly an important part of this process, is being able to do a visual representation of what's going on. So I'm just going to call us quits at this point and leave the rest for the next video. Cheers.